Hello, and thank you all for coming today, or thank you for watching the recording this week. As I had introduced myself in our introduction video that I posted earlier last week, I am Katie. I'll be your instructor. I am excited to see some friendly names from the last time we were all together. For those that may not know me, I am located in Minnesota. I traditionally teach some lab classes on campus up at Lake Elmo, but I also have a couple of 5.5 week courses. Those that may not have seen that in our 2100 course together, but physics and radiobiology are my bread and butter. I love it. I find it fascinating. So hopefully I can convey some of that towards you. I know this content can be a little overwhelming, so please, if you need help along the way, feel free to reach out. I am here to walk you through. Hopefully we can answer some questions or at least guide you to where you can find those answers. Before I dive in, I have a few announcements that I just want to go over to remind everybody. Make sure when you are doing your peer help for this week that you're posting it into Module 2. I did notice a couple recent posts back in the Module 1 peer help, so make sure you guys kind of go back, make sure you post it in your Module 2 so you can get points for this week. So again, peer help, make sure you're posting in that correct module every week. It's not just one peer help forum. Additionally, yesterday was Tuesday, so that was your due date for your initial post for your discussion this week, and then your reply post is due Saturday. So I know we have a couple stragglers with that initial post, so please make sure that you get that in so there's not too much of a point deduction. But here on out from 2 through 5, we have that initial post on Tuesdays and that reply post due by Saturday. And then all of your other assignments are due on Sundays. I know there's a lot of assignments. There's a lot of content that covers and gets you kind of looking at different perspectives and applying the knowledge that we've learned through our previous classes into kind of application of what is actually happening to the human body if we're not following our protocols, right? So naturally, we're not going to do anything to harm our patients. Well, at least we shouldn't. That's not our goal. We have that risk versus benefit that we have to go off of. And right now, x-rays are more beneficial than there are risks, but we still have to understand those risks. So our radiobiology course and radiation protection course, excuse me, there's both of them, is going to go through all of that. This week in our live module classroom, or live classroom module, excuse me, I'm going to talk about chapters 4 and 5 in your textbook. I have already posted a PowerPoint covering chapter 3. You can find that in the module 2 folder on our Blackboard page. So make sure you check that out. I have also posted a handful of videos. The videos are going to help break down radiation measuring. I know there were some questions versus dose equivalent and effective dose. We also talk about that in the PowerPoint today, but there's a couple videos that will help differentiate that. And I believe one of the 4 of you that are here today posted about this last week, but I can't be for certain. Alpha, beta, and gamma particles. I have a video that posted into module 2 that might help break some of that down. I know that was a question in one of the peer helps. So hopefully we can get some more knowledge kind of building. I love the questions that you guys are asking each other. So keep it up. Hopefully we can kind of tie everything in. I do try and reach out and answer some questions along the way. Otherwise, we'll just get right to it. So in module 2, I first want to review kind of what we went over last week, the videos that you guys watched. So the 3 Mile Island and Chernobyl. Fascinating. At least in my mind, it's so unfortunate, but it's still very much a fascinating disaster, or 2 disasters that have occurred. I know one of your classmates had posted or asked if there were any policy changes because of these, and unfortunately, not one that are made publicly, at least. I'm sure there are some businesses that have really cut down on what's happening and have really strict or provided strict rules. So hopefully there have been some changes in different businesses, nuclear businesses, but I have these pictures posted. The one in the bottom, that one is actually posted from the Chernobyl series. I believe HBO did it. If you haven't watched it, super fascinating. In our course announcements this week, I had also posted another video about not necessarily a radiation nuclear disaster like these were, that we had watched for our discussion post, but it is on a story called Radium Girls, and that was here in the US. Extremely fascinating, kind of blows your mind at what um, was real or what was perceived as being okay. So if you haven't watched that little clip that I've posted in the course announcement, I would suggest checking it out. If you're interested in another sort of radiation exposure that essentially they were telling um, the public that radium was okay. And we know now that radium is a radioactive particle that decays and is very damaging. So take a look at it. There's also a movie out there. Again, something else to check on. But moving on from that, I want to review the 15% rule with all of you. So when we talk 15%, that is when we're going in and we're needing to make changes to our technical factors. Typically, when this happens, we are looking at maintaining our receptor exposure, but we're needing to change our KVP for whatever reason. Be that we need more penetrating power or we need a shorter time. We are making those changes. Technically speaking, our 15% rule states that if KVP is increased by 15%, that 15% increase has the exact same effect on our receptor exposure as if we were to double our MAS. Likewise, if we were to decrease that 15%, that KVP by 15%, it'll have the same effect on that receptor exposure as if we were to cut mass in half. So that 15% change, that very minimal percent change in KVP has a very large effect on our receptor exposure. So knowing this, we develop it into how are we going to change these technical factors to maintain our receptor exposure. We like the first image that comes out, but there's, some minor tweaks that we have to do with it, but all in all, the exposure itself was good. So if we were to increase that KVP by 15%, then mass should be reduced by half to maintain that receptor exposure. And again, that is because KVP, that increase of 15%, is equivalent to doubling that mass. So in order to maintain, you have to half that mass. Whereas if KVP decreased by 15%, then MAS should be increased by 2 or doubled to maintain receptor exposure. Let's do a couple problems together. It's been a little bit since we've had physics, maybe a little bit since we've actually done these problems. Let's do a little refresher. So, example 1. An image is taken using 80 kVp and a 10 mass. The X-ray beam is too soft to penetrate the body. To increase penetrating ability of the X-ray beam, but maintain that receptor exposure, what should the new technique be? So I always tell my students, look at the question, what is the question asking you? Or what is the question telling you? So firstly, I know that my initial X-ray beam is too soft. Okay, so now I'm instantly thinking about too soft. What does that correlate with? What type of KVP is that correlating with? Then I know that in my new technique, I need to increase my penetrating ability. Again, using my vocabulary or my terms that all are related to one another that I learned back in physics are kind of running through my mind. Then lastly, I know I want to maintain that receptor exposure. So these 3 items tell me that I need to increase KVP by 15%, and decrease mass by a half. So there's two ways that we can change our KVP. Whichever way is fine, they come up with the same answer. First one, I call it the longhand, would be you take your initial KVP and multiply that by 0.15, which represents that 15%. That number is 12. And because we are increasing that initial KVP, you're adding that 12 to that 80 to equal 92. The shorthand way would be to multiply 80 by 1.15, and that goes right to 92. Long explanation short, when you multiply a number, in this case, we're multiplying 80, and we want to increase by 15%. If we take 80 multiplied by 1, that is 80, and then we know that 0.15 is 12. So essentially, you are combining this two-step process into a one-step. Both options are great. Both options are good. You don't have to do one way or another. You still get the same answer. And then we have to find our mass, and we said that that needs to be reduced by half. So we take our initial MAS of 10 and divide it by 2, getting a mass of 5. So the new technique, in order to increase that penetrating ability, we have increased our KVP to 92, and we have decreased our mass to 5 in order to maintain that receptor exposure. All right, I got one more for you. This time we have an image taken at a 90 kVp and an 8 MAS. But this time the beam is too hard and too much of the X-ray beam is penetrating the patient. To decrease penetrating ability of the X-ray beam but maintain receptor exposure, what should the new technique be? So what are some of those items in that question that are guiding us to how we need to find our answer? The first one that stands out to me, yep, you're both right. We have our too hard of an X-ray beam. We are looking to decrease that penetrating ability. And we are looking to maintain that receptor exposure. So decreasing KVP by that 15% is going to be our answer. And because we are decreasing, we need to double that mass. So again, showing you option 1, decreasing 90 multiplied by 15% is 13.5. So subtracting that to get that new KVP. Second option, this time you subtract the 0.15 from 1 to get your 0.85, and that finds your answer from there for option 2 for the shorthand. And then naturally multiplying our mass by 2 to get 16, with our new technique being 16 or 76.5 kVp and 16 MAS. Many of you, it might be like riding a bike to get that back into the swing of things, thinking about it. Some of you, it might still be a little bit challenging. Let me know. I can always help you out with some more examples if you need. But going over this is going to help us understand kind of what's going to be happening with our radiation quantities and our measuring that we're going to be talking about here shortly. So in chapter 4, we cover radiation quantities in units. Before we really jump into those quantities and units, I want to give us a little history replay. I know we have heard this time and time again, but I want to say it again because it'll come up. I can't tell you how many times students have come back and said, Katie, Rankin was actually on my boards. I can't believe it. His information was on the board exam. So Wilhelm Röntgen in, as we know, 1895, or on specifically November 8th, he had discovered X-rays. He took the first X-ray of his wife's hand, and many early pioneers of radiation researchers developed effects from radiation exposure because they had no idea that what they were working with was harmful. So they exposed themselves over and over and over again, thinking, wow, this is so cool. We get to look inside of ourselves. We're seeing our bones without realizing what was happening. So everything that we have been taught by Rankin and his first X-ray image of his wife's hand. There we go. I was trying to click a couple times and it didn't go. Everything we know about this first image leads on to our very first American fatality due to radiation exposure. This gentleman in front of you is Clarence Daly. He was Rankin's right-hand man, um, as well as Thomas Edison's right-hand man. He died at the age of 39 due to metastatic melanoma. He was listed as the first American radiation fatality. Um, you can see in the half the image on the right that he is holding his hand under a box that is containing an X-ray tube, while that gentleman with his eyes in the box is Thomas Edison and is examining that hand through a fluoroscope that he essentially invented. So they utilized Rankin's ideas and had developed a fluoroscope. So unfortunately, they didn't really put two and two together for quite some time that Clarence Daly died of radiation exposure. So we have taken everything that we know now, and it's all been based off of what Rankin has told us in these events back in the early 1900s, and it has showed us that we really need to be aware of what radiation can do. And I don't remember if you guys remember, but I think it's right around 10 to 15 minutes in length was how long it took for that hand x-ray of Mrs. Rankin to expose to see those bones. And this was supposed to be great quality back then. So we have really come a long way in our image quality, but we have come even a longer way when it comes to exposure time. Right? We are nowhere near using 10 to 15 minutes in length. We are down to milliseconds. That's how we are measuring things. So our radiation exposure today has greatly changed, but we still base a lot of content off of these instances. So because of that, there was a need to develop standards in order to measure and limit our radiation exposure. This standard, or this development of standards, was bringing awareness of potential harmful effects of ionizing radiation. It was also pretty desirable in the medical community so that we could reduce that radiation exposure, but that we wanted to utilize it for medicine too. So throughout the world, by developing these standards, we were able to bring it strictly into the medical community. And this is the reason that diagnostic imaging personnel need to be familiar with radiation quantities and units because of these standards on how we're going to measure and limit that exposure to our patients, but still getting that diagnostic effect. So when it comes to ionizing radiation, this box 4-1 is found in your textbook. But we want to first look at the somatic effects. Do any of you know what a somatic effect means? essentially, who is this affecting? And it's okay if you don't know because we're going to talk about it. All right, so it is, yes, the patient or the person receiving the radiation. So our early deterministic somatic effects versus our late deterministic somatic effects, those are your short versus long-term effects. So early somatic effects, that's going to be, again, all of these are really based upon high doses. But the early effects can happen instantly or within a handful of hours. I believe they even say up to a few days is still listed as an early effect. So that is your nausea, your fatigue, your fevers, your loss of hair, specifically redness in the skin. For those of you familiar or slightly unfamiliar with radiation therapy, we utilize a very high dose of x-rays to um, essentially kill or treat cancer cells. Because it's such a high dose, those individuals that are receiving that radiation for that specific area could get redness in that region because of the treatment center. There are some effects that do happen, but they typically essentially quote unquote wear off or they work past them. The late deterministic effects, that is going to be your cataracts. So a radiologist, if they aren't wearing protective eye gear and they are next to a fluoroscopy machine a lot, can have cataract issues. Sterility or reduced fertility could occur when you're around radiation far too much. And of course, cancer could result. Also, genetic effects or your hereditary effects that can be passed on to your next generation. So, with this in mind, we want to look into measuring our dosages, okay, and how to measure those dosages. So back in the early 1900s, so 1900 to 1930, we had dose measuring known as skin erythema dose. And that essentially was how much dose is going to create redness on this individual's skin. Really, that was it. They waited until the redness showed up. And what we know now that that's almost a little too late, right? There's some areas that we can help and come back from, but others that ends up being far too much radiation. So then shortly after that, there was something known as the tolerance dose, and that was considered the radiation dose to which occupationally exposed individuals, so ourselves as future rad techs, could be exposed without any apparent harmful acute effects. Okay, so that would be your erythema or redness of the skin. The general belief of this was that there's no adverse effects that could occur below that level, that threshold level, for injury to that exposure. So basically, a search for a more reliable unit to replace this tolerance effect was put into place. And that began as scientists started to recognize these late deterministic somatic effects that we just talked about and late stochastic effects. So then in 1950, MPD, maximum permissible dose, was utilized, and that replaced tolerance dose. Basically, it indicated the largest dose allowed to occupationally exposed individuals. It also indicated that no amount of radiation was considered completely safe. Just that the probability of injury was lower if they stayed below that level. Then in 1977, dose equivalent replaced MPD, and that indicated the largest dose allowed for occupational workers. And today we utilize effective dose, and that measures the risk from exposure. So we are going to talk about our dosages. First and foremost, let's take a look at our actual radiation quantities and SI units of measure. We have exposure, air kerma, absorbed dose, equivalent dose, and effective dose. Exposure is measured in coulombs per kilogram. Air kerma, gray in air, that is where you can see the little a. Absorbed dose is gray in tissue. And then both equivalent dose and effective dose are measured in sieverts. So we're going to dive into each one individually. Hopefully that helps clarify some differences between these. But starting with exposure and air kerma, exposure is the SI unit of measure for radiation quantity, okay, which is our exposure, is equal to an electrical charge of 1 coulomb produced in a kilogram of dry air by ionizing radiation. That is what our textbook tells us. It's used for X-ray equipment calibration and is used to calibrate radiation survey instruments. So this is a calibrating measurement, whereas air kerma measures energy of the ionizations in the air. So this is what is generally replacing exposure. So we're slowly removing exposure and moving into air kerma. Basically, air kerma is how much radiation is coming out of the X-ray tube and going towards that patient. We utilize this to also measure leakage radiation out of that X-ray tube. So both of these are prior to interacting with the patient. Now getting into absorbed dose. This is the amount of energy absorbed by a structure that depends on the atomic number. So the atomic number of the tissue, the mass density of the tissue, energy of the incident photon. It indicates the energy that the patient actually receives. So this is the amount that the patient is receiving. We go off of absorbed dose and know that it's responsible for any biologic damage resulting from exposure. It's used to report our patient's dose. Again, it measures how much radiation is absorbed by the body. Something that we always need to remember, though, is that some structures absorb more radiation than others. So this is just a generalized term. Okay, so this is just the body absorbing it. We're not taking those structures into account when it comes to absorbed dose. However, we start taking those tissues into account when we talk about equivalent dose. So equivalent dose compares harm of radiation based on the type of radiation. Okay, so not necessarily where it hits the patient, but the type of radiation. So our textbook explains that it's the product of the average absorbed dose in tissue and its associated weighting factor chosen for the type and energy of radiation. So you take your absorbed dose and you multiply this factor to arrive at your equivalent dose. So you look at this table that is on the right. It's also found in your textbook, but you can find that X-rays and gamma rays have a radiation weighting factor, or WR, as 1. So essentially you take your absorbed dose and multiply that by 1, and that is your equivalent dose. This is how we are documenting our occupational exposure. Yes, it seems kind of redundant to measure hours as millisieverts versus going with the absorbed dose, since we're just multiplying our radiation weighting factor by 1, but we utilize the same measurement or occupational exposure measurement as everyone else that is coming in contact with X-rays, gamma rays, and all ranges of nuclear radiation. So yes, ours is equivalent to absorbed dose, but it's because it's on its own specific scientific factor, I guess you could say. So how does equivalent dose differ from effective dose? We actually utilize them together. So the definition of effective dose is the sum of the weighted equivalent doses for all irradiated tissues and organs. It provides a measure of overall risk of exposure. So what we do is we multiply our absorbed dose by the radiation weighting factor, so what we just talked about on the last slide, and then we multiply that number by the tissue weighting factor. So on the table on the right, you can see the weighting factor for several different tissues and organs. So you have your colon and you have your bladder and you have your liver and your skin. They all have different weighting factors. So in order to find your effective dose, your overall effective dose, they take the equation at the bottom and they add them together. So say, I'm just going to go with something. I am affected or I have just been in contact with radiation and it was strictly at my thyroid down to my diaphragm. Okay, so I have in here, mouse here, there we go. So because I was exposed from thyroid down to my diaphragm, I would have my esophagus, my thyroid. I would want to look at the skin. I would probably say bone surface to a point, my breast tissue, and my lung tissue, hands down. So I would utilize these weighting factors and utilize the 1, 2, 3, 4, 5, 6 different categories and add those 6 together at the end. So I would answer each question based upon, okay, the lung tissue. Now I have my answer and say it is 15. And now I have my breast tissue and that answer is 2. And I have my thyroid answer and that effective dose is 3. So I'm going to take that 15 plus 2 plus 3 to get my summative effective dose for that region. Does that make sense? So you can look at the tissue itself and only that tissue. But if you're looking at a region in the body, you have to take in each different tissue and organs factor into account and you add them all together. So the difference, going back and forth, the difference between effective dose, you are taking into account the radiation weighting factor, so the type of radiation, and you are taking into account the tissue weighting factor, so the type of tissue or organ that is having that radiation detriment. Whereas your equivalent dose is only looking at your radiation weighting factor in addition to that absorbed dose. So all of these measurements are extremely important for us because we can figure out how is this going to affect our patients or what do we need to do to maybe we find our air karma is really high and that our patients are getting high exposure doses yet our techniques are pretty low. So that's going to allow for physicists to come in and make adjustments or for your clinic or your hospital to make those adjustments to work with the equipment that they have, but also still protect their patients and not overexpose them time and time and time again. And that is why if you haven't looked, or if you haven't noticed, going from different clinics or different hospitals, you might see slight changes to their exposure factors or their KVP and MAS because they are taking these exposures that are happening inside of their department into account. And they're trying to keep the absorbed dose, equivalent dose, and the effective dose for their people as low as possible, which is where Alara comes in. Questions so far on Chapter 4. I know there was a question about the worksheet. Rachel, does the worksheet state, I can't remember off the top of my head, I can take a look, but does the worksheet state if it says round to the nearest whole number, 10th or 100th? I want to say it doesn't, but if you round to the whole number, that is completely fine. I'll take a look too, and I can send out an email on what I'm looking for, or, okay, perfect, Whitney, it does not. So then let's round to the nearest whole number. So if you're at 0.5 and above, you're gonna round up. And if it's essentially 0.49 and below, you're gonna round down. Because most of our techniques, you can't do the decimal place. So let's just round up to the nearest whole number. Fabulous. And before we dive into Chapter 5, I do want to talk about our live classroom code word, code phrase. Today it's kind of a two-parter. Two parts because first thing, reminder, you have a midterm that is part of this class, and that midterm is due to be completed by the end of the day on March 4th. You know, that seems like a ways away, but it's actually 2 weeks from now. Okay, so my question that I want you to answer is part 1, have you scheduled your time to take this exam? Whether that is the day that you're on lab, or if you're not on campus, have you already reached out to your instructor or somebody that is on campus that can proctor that exam? And question 2 to answer is, what day are you taking it that week? So I'm looking for a yes or no, have you scheduled it? Hopefully you all know what day and the date you are going to be taking that midterm. So for those of you that are not on campus, it would be advised to start reaching out to get that scheduled, to figure out when you need to be at campus to take that quiz, because these exams cannot be proctored via WebEx. They need to be done in person. So again, your code phrase, code word, you're going to answer the question, have you scheduled your time to take your midterm? Whether that is on your lab day or you're coming in on a different day because you're not normally on campus. And what date are you taking the midterm? Fabulous. So let's move on to Chapter 5. So Chapter 5, we are talking about radiation monitoring and radiation measuring. So monitoring personnel exposures. So that ensures that us, personnel, occupational personnel, or occupational radiation exposure people, that our levels are kept well below our annual effective dose. Okay, so again, effective dose is absorbed dose multiplied by radiation weighting factor. This monitoring creates awareness of various radiation exposure monitoring devices as well as their functions. So one of your assignments this week, you're going to be talking about dosimeters. And in our occupational life, dosimeters are required whenever we as workers are likely to risk ourselves to receive 10% or more of that annual effective dose limit. That annual limit for us only, occupational workers only, is 50 millisieverts. This monitoring provides an indication of workers' habits and working conditions of diagnostic imaging personnel. So working habits, meaning have you gotten your dose report back and have seen that there's a dosage in there? Are you being lax about being completely behind the lead wall, or are you wearing your lead shield while you're out at clinicals and doing a fluoroscopy exam? Or working conditions, we had a site that had high dose reports from a control dosimeter. And that dose report was telling them that their lead window that is by their control panel that they watch their patients through while they expose didn't have the proper lead lining. So all of their personnel had a high reading because radiation was still coming in towards that window. So it actually also helps determine, are all of the staff members receiving this? Who are receiving this higher dose or this exposure? And what is it in the working condition or the habits of that individual that need to be adjusted or need to be fixed in order to lower those doses again? And then keeping with ALARA, always, most healthcare facilities do issue dosimeter devices when personnel could receive approximately 1%. So most of your healthcare facilities, well, all of your healthcare facilities that you will be working at in the future will provide you with a dosimeter. But for individuals that out of the blue might be working with radiation, would likely get a dosimeter as well if they receive more than 1% of their annual dose. So our placements of a dosimeter. Yes, we know what this is, but I think it's good that we talk about it again so we can make sure that we are placing it in the right spot. The one that you've been given at school, you should only be given one at this time. That is worn up by your collar. Even when you are wearing a lead apron, you should be wearing it at that collar level, also on the outside of that apron. So always at the collar level, whether you have a lead apron on or not. But once you put that lead apron on, you still want that dosimeter on the outside. And the reason for that is that we are, we as in our RadTech community, so not just Rasmussen, monitor what you're exposed to, right? So if you were to put it underneath the lead apron, you're not necessarily providing accurate content to determine what you're actually being exposed to. So you could actually be exposed to much more if you are putting that dosimeter underneath that apron. So you want to make sure it's on the outside of that apron. However, if a second monitor is required, so typically this is done for pregnant individuals, but a lot of facilities are now providing a second monitor for all of their staff. And this one is going to be worn at waist level. So basically on the bottom of your scrub top, you can clip it there. And that is to essentially measure the exposure to the gonadal region or the reproductive system. When you wear a lead apron with that, you are going to put that one underneath the lead apron. So the one that's up on the collar is always on the outside. The one that is down by your waist is underneath the lead apron. Please also remember that we only utilize the dosimeters when you're working and not when you are going to be receiving personal medical x-rays for any reason. Do not bring that with you if you have broken your foot and you are getting an x-ray. Only have it on you when you are working as a rad tech. There are 4 common types of dosimeters. Okay, you have film badges, thermoluminescent dosimeters, optically stimulated luminescence pocket ionization chambers. These 4 dosimeters are likely to be one of the four are likely to be the ones that you talk about in your assignment for this week. Film badges are obsolete now. They literally had a piece of film inside of a badge, and based upon how that film was exposed was how much radiation you were exposed to. Thermoluminescent dosimeters, TLDs, they look similar to that same old film badge. Typically, they're used as an extremity dosimeter, usually worn as a ring. So sometimes you'll see a surgeon have a dosimeter on their hand because their hands are sometimes by the fluoroscopy machine, or even a radiologist that is in fluoro a lot might be wearing a TLD to measure how much dosage their hands are getting. OSL is optically stimulated luminescence. This is the most common one that we utilize in diagnostic imaging. And then pocket ionization chambers. These are very expensive. Essentially, the ionization chamber that we are familiar with are in our X-ray equipment. Do we remember where in our X-ray equipment these are and what they're used for? Another second to think about it. It's probably something that just kind of floats past you. But your ionization chambers are your chambers on your Bucky for your AEC. So there are 2 different types of AEC chambers that are utilized. You have phototimers and ionization chambers. The ionization chambers, essentially, when your AEC is triggered, right, your AEC is on, or you've selected that's the route that you're going to go, and you select your center cell or your all cells, you are essentially activating those cells or those chambers. And then when the radiation goes through your patient and it hits those ionization chambers, the particles on the inside ionize. And when the chamber fills completely with ionized particles, it shuts down the exposure and it times out. So a pocket ionization chamber basically is a little ionization chamber like that that you carry around, and it slowly ionizes the particles that sit inside of it. So all in all, of these 4 types, I want to make sure that you guys are reading this section, this type of dosimeter section in the chapter. Know the advantages and the disadvantages of each of them. I also want you to know what each of them is made out of and how they work. That might come in handy for your assignment, but it's also going to come in handy, for the midterm and the final for that matter. All right, so record of radiation exposure. Every employee should keep records of each employee about exposure levels. Okay, so everywhere you go, there's a record of your radiation exposure. Your boss has it, right? So your program coordinators, so that's Crystal and Renee and Lisa and Dawn. Those 4 individuals are our program coordinators, and they each have your records of radiation exposure, as well as every quarter or every other quarter, you will get your radiation dose report. We'll talk about that in a moment. Your employer receives that report from the company of your dosimeter, and the results are kept in your file because they utilize that to monitor your lifetime dose. So even if you move from one hospital to the next, or you as a student here moving into a actual career, if a job is looking for your radiation report, your program coordinator will be able to have that, and they will send it on to your next job, and then so on and so forth, so that your radiation doses follow you to ensure that you are staying in that acceptable dose limit. Your employer, so not you as an employee, but your employer is responsible for the cost of the dosimeter as well as the dosimeter maintenance. This is an example of a dosimeter report. Okay, so you see a dosimeter report on the worksheet for this week. One thing that I really want to point out outside of looking at each individual, okay, so let me activate my mouse again. Each individual is listed here along the left, and their dose reports going all the way across are made available. Okay, so you'll see the sex, you'll see the dosimeter. So this is what dosimeter was used, whether it was used as a whole body. You can see for Mike Jorgensen, there is a ring finger, whole body, whole body. Steve had collar, waist, ring finger, and then you have your control. Then coming across, you are looking at all different doses. You have your dose equivalent, you have your quarterly accumulated, the year to date, and their lifetime dose. So each 3 boxes on this report shows a different number and shows, as you're adding that content or adding that dosage to them, every quarter, every year, and then for their lifetime. You will also know that there are several M's in place, and that M represents minimum or minimal, meaning, and you can see that written here, that the report is less than 1 millirem. So essentially, minimum dose, not enough to report. Few things that I do want to touch base on before we wrap up today are radiation survey instruments. Okay, so this is a section in your textbooks that I want to make sure you guys are reading as well. But radiation survey instruments, these are gas filled. So ionization chamber survey meter, or QT-PI. It works very similar to the other ionization chambers that I had mentioned. Proportional counter and a Geiger-Müller detector. These are not personnel dosimeters. They monitor areas of radiation, not people. So they monitor essentially radiation that is exposing in that big area. So I believe I posted a video on specifically the Geiger-Müller underneath there. If I haven't posted it yet, I will post it here shortly. But it's showing everything that is basically surrounding us has some sort of radiation level, and it is measuring that area of radiation. Okay. Not necessarily what that person is getting, just what that general region is getting. So make sure you're reading these items in the chapter. Know the advantages and disadvantages of each of them and what each might be used for. Specifically, I want you guys to know about that Geiger-Müller, because that is used predominantly in nuclear medicine. Any questions before we wrap up our live classroom for the week? That is all I have for you. You know where to find me if you do end up having any questions. Send an email, post the question on Peer Help if you think it's a pretty generalized question. Hopefully some of you got some of your questions answered from your Peer Help. Otherwise, I do try and keep looking back and answering those questions. Yes, the PowerPoint is going to be posted. It'll be posted with the recording link. So under Module 2 folder, there is going to be a recording link, basically folder, and it's going to be posted with that. So you'll be able to get the PowerPoint as well as the recording. So you'll have access to both of them. I also want to mention next week, Module 3, we do not have a required live classroom, meaning there's not one that you have to do for an assignment. However, if you look on our course calendar, I have set aside some time the 24th, Thursday evening, to jump on to WebEx and answer any questions that anybody might have for the midterm, being that the midterm it would be the week after. So next Thursday, I'm going to jump on at, I think it was either 5 or 5:30 Central Time, so 6:30 Eastern Time, to answer any questions that you guys might have prior to your midterm. Next week, being that there is not a required live classroom, you will get a PowerPoint posted, or the PowerPoint is posted already for you to go through, read through that information to help you with your assignments, but also prepare for your midterm. But if that is it, I'm going to end the recording here and we will call it a day. Thank you so much.